Salam sejahtera to Encik Jais. I'm Kee Han, and my title of my final year project will be comparison of a silicon MOSFET, silicon carbide MOSFET, and gallium nitride MOSFET in EV charging application under the guidance of my supervisor, Dr. Muhammad Anas bin RAZALI. In this presentation, we're including the introduction, problem statement, objective, scope, methodology, result, conclusion, and including the recommendation for future work. First of all, we know that EV are replacing our conventional vehicles due to the zero emission and the decline of the non-renewable energy source. The main non-renewable energy source is the fossil fuel, and fossil fuel are the major carbon dioxide emission source. Therefore, EV offer an eco-friendly solution, but battery limitation hinder the adoption. Therefore, the wide bandgap semiconductor are able to enhance the charging and efficiency. The wide bandgap semiconductor have a larger bandgap for higher voltage, temperature, and frequency operation. So, in order to tackle the limitation and enhance the charging capability, the ongoing research has explored the integration of the wide bandgap semiconductors. These wide bandgap semiconductors offer the increased power density and efficiency, making them promising solution for EV charging application. And by address the crucial problem of enhancing EV charging capabilities by comparing the performance and sustainability of a silicon MOSFET, silicon carbide MOSFET, and gallium nitride MOSFET. This research provides a valuable insight to select the most efficient semiconductor technology for EV charging system. The first objective of this thesis first is to analyze the comparison of silicon MOSFET, silicon carbide MOSFET, and gallium nitride MOSFET in terms of their electrical characteristics as well as in the EV charging application. And second, to determine the device losses for these three types of MOSFET using specific formula. For the project scope, first is concentrate on the comparison of silicon MOSFET, silicon carbide MOSFET, and gallium nitride MOSFET in EV charging application. And second, simulation of each type of MOSFET with different specification, including a static drain, source on, state resistance, RDS on, drain current, ID on, turn on switching loss, EM on, turn off switching loss, EM off, and including the gate source voltage, VGS, input capacitance, CIS, reverse transfer capacitance, CRS, and output capacitance, COS, in MATLAB. And last, determination the most appropriate materials for EV charging application based on their electrical performance and losses in device. For the methodology, first, the project is implemented by MATLAB, and comparison is the electrical characteristic difference between the silicon carbide, and gallium nitride MOSFET. And third, simulate the reference model of charging topology in MATLAB. And fourth, analyze the output result as well as the output waveform. And fifth, determine the power losses of each type of inverter. And last, comparison the performance of the inverter based on the results. First, the simulation software using is MATLAB, including the Simulink extension. So in the right side is the specification for each type of MOSFET that be selected from their datasheet from different company. For example, like silicon MOSFET is selected for Infineon, and silicon carbide is selected for Wolfspeed. So have different datasheet from the different company. Here is the reference model for the output characteristic. So using the MATLAB example in this figure, the characteristics of N-channel MOSFET are methodically calculated, and the model makes it possible to observe the MOSFET behavior under various operating situations by applying appropriate input signal which facilitated a thorough knowledge of their dynamic property. Here is the charging topology we use in this simulation, which is a 3-phase and 180-degree mode inverter. So for the result first, comparison for the output characteristic. In this, first is figure for the silicon MOSFET, and second is a silicon carbide MOSFET, and the last will be a gallium nitride MOSFET. So we can see that, for example, we use the VGS6 as an example. First, we see that the gallium nitride able to produce a higher drain current, which is 24 ampere at 5 volts. Compared to silicon carbide, it only have 17 ampere when 5 volt, and the lowest will be the silicon, which is the only 5 only 6 about 6 ampere when 5 volt. So we can know that the gallium nitride able to perform well. And next, for the transfer characteristic, so we can see that based on the comparison, so we know that as the gallium nitride has a lower threshold voltage in order to turn on the MOSFET. So it only requires 1.74 volt to turn on the voltage, to turn on the MOSFET. Compared to silicon, it needs about 3.5 volt to turn on the voltage, the MOSFET. So which means that the gallium nitride require less energy usage. Next is for the gate pulse. So first of all, this means that when MOSFET 3, this one, is switched on, and MOSFET 6 will be switched off, or vice versa. And each gate pulse corresponding to a specific angle range of a sine wave produced. For example, MOSFET 1 handles the angle range from 0 to 60, MOSFET 2 handles from 60 to 120, MOSFET 3 handles 120 until 180, MOSFET 4 handles 180 until 240, MOSFET 5 handles 240 until 300, and last MOSFET 6 covers the range from 300 to 360. Here is the phase voltage and line voltage for the inverter. First of all, for the inverter, we know that his phase voltage is produced approximately 200 voltage for each phase, and for line voltage is approximately 300. So for the closer view, we take a peak from a line voltage here as an example. So based on a comparison, as the gallium nitride based inverter, which means represented by blue line, so it dropped the lowest. So from 300 it dropped until 299 and 0.847. And a silicon carbide based inverter also dropped a little until 299.817. However, for the silicon based inverter have a higher decrease, which drop approximately 0.5 voltage from 300 until 299.512. So gallium nitride based inverter have a best performance in this. Next, for the losses calculation, here is the equation we use for calculate. First of all, here is the total power losses for single MOSFET. Therefore, in an inverter, we have 6 MOSFET. Therefore, we need to multiply by 6. Here is a calculation for conduction loss, and here is switching loss. For the conduction losses, so based on the data we get, based on the value we get, the gallium nitride have a lowest conduction loss. Next, the switching loss versus the switching frequency. So we can observe that as the frequency increase, the gallium nitride MOSFET, the yellow, is increasing also, but it's more constant. So, however, the silicon MOSFET has a higher slope, which means that it increases rapidly. It has higher loss at a higher switching frequency. Next is total inverter losses. So silicon carbide have a higher losses, which is approximately 311. And second will be silicon carbide, which is approximately 302. And last, gallium nitride MOSFET inverter have a less total loss, which is approximately 270. So here is the concrete table for three losses. So we based on comparison of three losses, we know that the gallium nitride MOSFET perform well in all losses, so it has a less losses in all categories. For the conclusion, the gallium nitride MOSFET are most efficient for high frequency and high power density EV charging application, inhibiting the lower switching losses and capacitance value. And the silicon carbide MOSFET also offer a higher efficiency than traditional silicon MOSFET, particularly in a high voltage scenario. And last, the research support the adoption of wide bandgap semiconductors like gallium nitride and silicon carbide to enhance the performance and efficiency of EV charging system. Last, for the recommendation for future work, first, exploration of a hybrid system. The hybrid system may combine the high voltage tolerance of silicon carbide with the efficiency and higher switching speed of gallium nitride, which will be ideal for EV charging application. Second, for the cost effectiveness analysis, future research I recommend to perform a cost effectiveness analysis of a proposed approach, including the factor like scale of production, the cost of material, and the long-term benefit of increasing efficiency. And last, reliability and longevity study. The long-term stability and degradation tests of MOSFET under the different operating conditions are required to assess the behavior during their lifetime. That's all for my presentation. Thank you.